Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled SOP Implementation. Okay, so congratulations, you've made it this far. At this point is kind of a pretty big milestone in your education about digital electronics. Up to this point, we've thus far just been kind of discussing how digital electronics work, some of the theories and some of the basic properties of it. And now this is where we actually are applying what the purpose of digital electronics are. Remember what I said earlier? It's designed, they're logical circuits designed to make decisions for you. So you don't have to be there. You're taking this sensor information and this circuit is making a decision for you, and it's going to end up acting the way you want it to. And now the key is how do you create an expression? Okay, up to this point, I've just been giving you expressions. You're performing some analysis on these things to go ahead and see how they work, but you've never gotten an opportunity to create an expression. There's a bit of an art form to this. There's a systematic procedures that we're going to go through, but like I said, it's a bit of an art form. Some people have it. Some people are these idiot savant people that can just look at something and the idea pops in their head. You may not be one of those people, and you may have to put some effort into these things. And what I'm going to do is I'm going to show you guys some systematic ways. I'm going to put you through art school, basically. I'm going to show you some systematic ways to develop these expressions. Okay. And one of the things I love doing is just doing these dumb analogies. I liken it to catching a bear. Okay. What are you going to do with a bear once you've caught it? Well, bears can do awesome things. You could ride it. You could train it to fight. You could send it to law school. And if it flunks out of law school and all those other things, at worst, you could just eat the thing. But the problem is it takes a lot of effort to catch that bear. What I'm saying is you got to go to where the bears are. You got to know what a bear does. You've got to construct a pretty sturdy trap to catch this thing. And I want this thing live. I don't want it dead, and I want it with all 4 limbs attached. So you got to build this sturdy bear cage to catch this thing. Some of these things I'm going to show you is you're going to have to put some effort into understanding this thing, because if you want to catch that bear, you're going to have to build a sturdy bear trap, and you got to know a little bit about bears. Okay, so we're going to talk about bears right now. We're going to talk about the SOP expression. And I have talked to you guys a little about the SOP expression. I'm kind of gearing you up to this thing. Basically, all expressions can be put, all combinational logic expressions can be put into one of 2 ways. An SOP, a sum of products, basically ands feeding an or a POS, product of sums, ors feeding an and. It is easier for you to understand an SOP. It is, and I'll show you why it's easier. It is easier for you to understand. No digital electronics course would be complete without the instructor totally confusing the student. So I am going to introduce the POS, but I'm very, very, very briefly. But we're going to deal primarily with the SOP. What is an SOP? Obviously, it's ands feeding an or. Okay, and the diagram I'm going to use is this just basic SPLD PAL ands feeding an or diagram, because it's pretty simple to use. All right, there's 2 things we got to do to talk about the SOP expression. Is basically taking an expression and putting in a truth table, and then doing that in reverse, truth table into an expression, and it doesn't matter which one. A truth table to expression, expression to truth table. You choose whichever way you want to, and if you want to do the other one, just fast forward to that section, do it, and then come back to this one. Okay, let's start off. Let's do expression to the truth table. Okay, so I'm going to go ahead and make an expression, see what we can do for how we put it in the truth table. And we'll use the same example for both of these things. So I'm going to go from expression to truth table. There you go. I've made some tiny connections there. What is our expression? It should look like this. There you go. A and B, or A and C. Okay, now that I know it's the sum of 2 product terms. The double underline being the product terms. It's an ands feeding an or. It's not a real SOP expression. What I'm saying is it's not the full-blown SOP expression, because it does not account for the full domain. What is the domain of this expression? It's the variables that matter. A obviously matters, B obviously matters, and C obviously matters. I know I've got D inputs on this SPLD, but they're not connected to anything, so D is not in the domain. Okay, does that make sense? It's the variables, so the domain is the variables that affect it. A full true, honest to goodness, big ol' SOP expression has to have all variables in every single product term. Okay, does that make sense? I have to somehow expand these things into the realm where the product terms include A and B and C for every single product term. This one's just got A and B, this one's just got C. Okay, so how do I expand these things? And this is kind of, we're taking this slow here. We'll go ahead and you're going to be able to do this pretty fast, pretty quickly, once I show you this through a couple times. Your understanding of this one, it's kind of based off of one of the Boolean rules that we've thus far discussed. Remember, A or not A, it's always equal to 1. And A and 1 is always equal to A. So if I multiply, i.e., if I multiply any of those product terms by this, I'm really in effect multiplying it by 1. And if I multiply by 1, I haven't changed it at all. So let's take this first product term, A and B. It doesn't have the full domain. It doesn't have the C expressions in there. How do I do that? Well, I multiply it by 1. A and B ANDed with 1. I'm going to leave some space because I'm doing one product term at a time. What's 1? Well, this is 1. C or not C because of this Boolean rule, right? What do I get? If I distribute A and B into parentheses C or not C, A, B, C, or A, B, not C. And I'm left with my original second product term. Okay, so I've expanded it. I've expanded that single AB term out to ABC, AB, not C. What do I do with this guy? I've got to expand him to include all of the domain. What is the domain? We've already figured out it's A, B, and C. How do I make use of the property A or not A is equal to 1, A and 1 is equal to A? Well, just take those A's and make them B's because that's the thing it's missing. I can multiply that times 1 or AND it with 1. What's 1? B or not B. What do I get as a result of that? A, B, C or A, B, not C because I haven't really done anything with those. Distribute that A, C through there. I'm going to stay in alphabetical order A, B, C or A, not B, C. Okay, am I at the full-blown SOP expression? Yes-ish, but look, there's duplicate terms. A ANDed with B, ANDed with C. A ANDed with B, ANDed with C. Does it affect this expression if A or A is equal to A? What if I just got rid of that thing? Rid of one of them. Here is my SOP expression. Here's my full-blown SOP expression. All I did was just get rid of one of those A, B, C terms. Okay, so we are finally at the full SOP expression. Now, since I've got written out, I'm going from the expression to the truth table. How do I take that full SOP expression and put it in the truth table? One of the ways to do this is to think of the binary equivalence of the individual product terms. So the binary equivalence of the individual product terms that make it a 1. Okay, and that's what the SOP expression is. SOP, think of make it 1. When I say it, the output. Make the output a 1. How does the product, that individual product, make it a 1? Let's say that's yellow, that's green, and that's pink. Let me clean up the rest of this. How does the yellow product term with the inputs A, B, not C become a 1? Well, what if A was a 1? And I'm going to write this off to the side. And just think of it as an individual gate, because it really is. It's an AND gate. I've got the inputs A, B, and C. How does that yellow term put a 1 on the output? Well, A could be a 1. I have to do nothing with it. B could be a 1. I don't have to do anything with it. Not C. So it means there's an inverter between C and the input. How do I make, again, what am I looking for? I'm looking for that right there. How do I make that output a 1? Well, if there's an inverter in the way, make C a 0. So the input to the AND gate is a 1. And what's the output of an AND gate when all its inputs are 1? It's a 1. So that's called the binary equivalent of each individual product terms. I'm going to say, I'm going to put it off to the side. I'm going to say yellow, A, B, C. The value for A should be a 1. The value for B should be a 1. The value should C be a 0. Do the exact same thing for the gate in green. How does A and B and C output a 1 if I put it on that particular gate. Well, you don't have to do anything with it. That's easy. A1, B1, C1. What's the output there? 1. So that combination for green is 1, 1, 1. Too easy. What's the next question? Obviously, how does that expression in pink, how do we make an AND gate with a not B, C output a 1? Okay, so we want A, not B, C. How do we make it output a 1? Well, put a 1 on A, put a 1 on C. And if I want a 1 right there, on the input of the AND gate, how do I make a 1 there? Put a 0 there. So that combination is 1, 0, 1. And you already see how to do this. You already may see how to do this. If that expression, if that individual variable, let's say, for example, our yellow term, A, B, not C, if the individual variable, say, for example, A, is not inverted, i.e. it's original, just put a 1 there. If B, it's not inverted, put a 1 there. If it's C, it's not C. If it is inverted, put a 0 there. Ultimately, I can come up with binary expressions that would make this true. And let's go ahead and take these values, and this is kind of the punchline. Take these values. Those make it a 1. Find them in the truth table, where A is 1, B is 1, C is a 0. Put a 1 at the output. When A is a 1, B is a 1, C is a 1, put a 1 there. A is a 1, B is a 0, C is a 1, put a 1 there. All the rest of the terms make it a 0. And now before I turn you loose on this truth table, I know it seems like I made it bigger than my original expression. It seems like we're doing the opposite of what we did in our last discussion about Boolean simplification. Yeah, we are we're expanding it out. We're coming up with the SOP expression, which is the full expression accounting for all the domain. No, we're expanding it. This is an exercise to get you to used to how the SOP expression is being used to put into the truth table. We'll go from the truth table to the expression, and then what we're going to be able to do is we're going to take any truth table. This is what I'm telling you about the bear trap. We're going to be able to take any truth table with a little bit of effort, with a solid, strong bear trap. We're going to be able to catch some pretty big bears, because check this out. I can make any truth table for any expression and come up with a minimum SOP expression. And the minimum SOP expression through a systemized method, what I'm going to use is called a Carnot mapping method. There are other methods. You're more than welcome to use them. I'm going to teach the Carnot maps. It's the easiest to learn. It's extremely versatile and powerful. You're going to come up with a minimum expression. And those Boolean rules that we learned, it's almost like you only need to kind of go back to them in emergencies. And again, it's a very specialized case. You got to build a bear trap. You got to spend some time doing these things and use these methods. But I digress. Let's go ahead and put this thing in the truth table. And I'm going to leave a trap for you in the truth table. Okay, so we got A1, B1, C0, and just read them off. They're right there. I want you to take those 3 values and put them in that truth table. Where's the trap? Some of you guys are going to be like, okay, I'm going to do this. I'm going to take A1, B1, C0. And you're instantly going to go there, you're going to go there, and you're going to go there. And your answer is wrong, okay? Why? Look at the heading of the truth table. It's CBA, exact opposite of this orientation. You can do it that way. You can't do it the way I just said right here. You can convert these things. You can take that CBA. Okay, so this first one, that yellow one, is C0, B1. A1. Okay, that green one is C1, B1, A1. The pink one is C1, B0, A1. So the real implementation of these things, the real correct position of these things in this truth table is that occurrence. Oops, let me use the correct color. That occurrence right there, that occurrence right there, and finally that occurrence right there. You can do that. You can do that back and forth if you want to, but what I'm saying is stay organized. The other thing is, why would you want to do that? Why would you ever want to make life complicated? Because check this out, you have not filled out that truth table. It would be just so easy to say ABC. Now what I put in is wrong, unfortunately. So I'm going to go ahead and do 2 truth tables, CBA, ABC. You're going to get the same values, okay? So the same correct one. Okay, so what I've done is done 2 truth tables. And this is what we originally came up with on the right-hand side, those expressions. And then this is what we flip-flopped them back around to fit the truth table. What I'm saying is just do this as an exercise. See if you can fill out both of these truth tables. They're the exact same truth tables, they're just ordered differently. ABC, just look for the combination 1, 1, 0. CBA, look for the combination 0, 1, 1. The same spot in the truth table, I just ordered it differently. The other ones really don't matter because you can't really flip-flop that one, can't flip-flop that. And just by luck of the draw, 101, 101. They're different areas on the truth table strictly because they're ordered differently. Now, put a 1 where those are. What's the rest of the truth table? 0, 0, 0, 0, 0. Because again, an SOP expression is looking for ones. So what we did was we took our expression, original expression right there, we expanded it to all elements of the domain. How do we figure out the domain? Well, there's an A, there's a B. There's an A, but we already counted for it. There's a C. So my domain is A, B, C. What if there was a D in there? Well, my domain would include a D too. I've got the final SOP expression. I figured out what makes it a 1 for all of those product terms. I took those individual binary representations, I put them in my truth table, but I gave you that truth table, so you got to do some flip-flop, but because I'm a nice guy, I allowed you to rearrange the truth table for that. The point of the matter is when I set you up for an exam or sit you down for a quiz or a lab, do the combinations in the way the truth table is organized. That way you don't get lost, and it becomes super critical. I mean, you can't put your bear trap upside down. It won't work. The bear's going to climb out. What I'm talking about is these Carnot maps, which we'll be working later. It is super easy to stay organized. It is super hard to use these things to use a K-map when you're disorganized. Ultimately, these two truth tables are the same. So what we've done was we've taken our expression, put it in a truth table. Let's learn a little bit more about bears and let's go backwards. And I'm using the same example, and I know you know the answer. Let's take our truth table and go to our expression. So let's wipe out everything that we've done thus far and come up with the expression from the truth table. We wiped out all our previous work with the exception of what you originally started with there. I'm going to actually go ahead and keep that so that way we know once we've taken that truth table, put it into expression, done some simplification, we're going to come back with that same one. I'm going to put that over below this guy that's riding a bear for some reason. Okay, so that is our, ultimately, when we do this thing, taking it from the truth table, we should come back to that. All right, so let's use the truth table on the right here. So someone gives you that truth table, A, B, C. We're not going to use this one over here. You can come back, and again, you can do the same thing. You can do this exact same thing and you come up with the same answer. You can try that a little bit later. But now we're going to go ahead and look at the truth table A, B, C. And I've already highlighted the ones. To convert a truth table to an SOP expression, look for the ones. What are the binary combinations of ones? Well, they're listed. 101, 111, 110. What if there's an output 1 there? For those combinations, what would an AND gate look like if those inputs were being fed to it to get it to produce a 1? Do you understand what I'm saying? How would combination, let's take our yellow, so let's take our pink one since that's the first one. How does the combination 101, how would, and that's being A, B, and C, how does that AND gate produce a 1? Well, A is a 1, don't do nothing to it. C is a 1, don't do anything to it. B is a 0, it looks like I gotta invert B. So that expression is probably gonna be A, not B, C. So A and not B, C. Do the exact same thing for the term in yellow. If, do that over here, this AND gate is going to produce the output 1 when A is 1, B is 1, C is 0. How do I make that? How do I feed those inputs to make sure that the AND gate gets a 1 and a 1 and a 1? Well, because the only time its output is high is when all inputs are high. Well, everything's high. A is a 1, B is a 1, but C is a 0. What do I got to do? I got to invert it. So that sounds like that expression is, again, let's call that, let's do this in yellow, in that previous one. That was the one for the pink. It sounds like that expression yellow is A, B, not C. How do you do that for the green? I'm going to take an AND gate. I want it to have a high output when A is 1, B is 1, C is 1. I don't have to do anything with it. What's the expression in green? A ANDed with B, ANDed with C. What's the sum of products. It's a sum. It's an ORing of those three individual product terms. A, B, not C, or A, B, C, or A, not B, C. Does this look kind of familiar? Maybe for the final SOP expression we had for when we took the expression and expanded it out? Certainly does. Does it look like our original expression, which we started with right here? No, it doesn't. How do we get there? This is where you've got to go ahead and do the Boolean rules and simplification. Okay, the real point of this lecture is to kind of get that SOP expression. We don't necessarily need to worry about simplification, but since we're here already, let's do the simplification. You're going to come up with AB and AC. AB or AC, which is what you started with originally. All we're looking for, what you really need to worry about right now is this SOP expression. This should be child's play right now. Well, not necessarily child's play. You got to use your Boolean rules and laws. Great example. Let's try it. Okay, pull out your Boolean rules and laws. What am I going to do? I'm going to look for a chance to maybe factor out something. I got an A and a C, A and a C. They're common terms there. Why don't I just factor out A and C out of those guys? A and C, B or not B. Oh my gosh, that looks like something useful. What is that? Well, due to our property of A or not A is equal to 1, I could just make that a 1. Due to our property of A and 1 is equal to A, I could just bring that down like that. See something in there, they could potentially factor something out. Why not remove that A? I'm left with B not C or C. So I've factored out A. Do you see something? Maybe if I did a little commutative rearrangement. Rule 11. What is that? That's A or not A, and it with B is equivalent to A or B. What am I getting here? It's C or B. I said to myself, number 11. A, is that our final expression? No, I want the SOP, sum of products. Right now I've got the product of sums, which we'll go into later, very briefly. Distribute that A in A and C, or A and B, which that dude on the grizzly bear is stepping on right now, okay, which we originally came up with. That was a little bit of a review of the Boolean rules and law simplification, but the key point is taking that truth table, which I gave you over here on the right-hand side, and making an expression out of it. All you do is, just like we did previously, find where it makes it a 1. Take those combinations. Think about this. 1, 0, 1, ORed with 1, 1, 0, ORed with 1, 1, 1. What do I got to do to make this one a 1? I got to put a negation over it, a negation over it. What's that combination mean if I'm going in the order of A, B, C, A, B, C, A, B, C? I got to negate that one. I got to negate that one. That's a real simple way of writing that expression. Then you got to go through all the Boolean simplification and to get it to that A, B, or C, or AC, if you wanted to do that. Right now, get it to the full SOP expression. We've talked a little bit about getting the SOP expression from truth tables, getting the truth tables from the expression. Let's do one more example of this. And again, it takes practice to do this. Okay, before I go on to another example, though, I want to show you a real quick shortcut. Some of y'all may get this, some of y'all may not. If you got an expression to put it into the truth table, just go ahead and just delete this truth table here. And because it's empty, I can order this any way I want to. I can always use my multi-level logic circuit analysis techniques that we've discussed thus far. I don't have to bring it all the way to the SOP expression. All I do is just figure out when that expression makes a 1. It makes a 1 when A is a 1 and B is a 1. Find where in the truth table where A is a 1 and B is a 1, because I know that due to the properties of ORs, anytime any input's a 1, what are the inputs for the OR? Well, it's A and B or A and C. So anytime, and this is what I'm saying, there's a little bit of an art form here. If you can look at this expression, directly go right straight to the truth table. You don't have to worry about that whole SOP expansion. When is A and B simultaneously high? Right there and right there. Put a 1 there. When is A high and C simultaneously high? Right there. It's the exact same truth table as we have right here. So that's a little bit of a shortcut right there. You might be able to see what I'm talking about. You might not. It's hard to do that when you've got some nans and nors in there. It's super easy to do that if you've already got a minimized SOP expression. But I digress. Let's go ahead and go on to our next full-on example. And I do want you to put this thing into a full-on SOP expression. Here is our SOP expression. Come up with the expression first. and then put it into a truth table. Okay, so let's do this in stages. First AND gate, what's it doing? A and not B and C. It's being ORed with not A and not B. Third AND gate, what's that doing? A and B and not C and D. That is our expression. How do I put that into a truth table? Before I put that into a truth table, what's my domain? What are the variables that matter? A matters because that's in all the expressions. B matters because that's in all the expressions. C matters because that's in two of the expressions, two of the product terms, and D matters because that's in one of them. So it looks like I've got to expand this thing all the way out to D for every single product term. How do I do that? Let's take the easiest one first, this guy. How do I expand just that product term out to include all members of the domain? Well, multiply by 1. What's 1? Well, maybe D or not D. That's equivalent to 1. So what I'm going to do is I'm going to expand out that first product term, A, not B, C. I'm going to multiply it or AND it with D or not D. All the other ones remain the same. What do I get? A, not B, C, D, or A, not B, C, not D. All the other ones remain the same. Whoops. There you go. And I know some of you guys might be doing that shortcut trick that I just showed you here earlier. Let's come on, just pay attention. I know you can do the shortcut. Try this. Gonna run into a little bit of difficulty here because look at this one. How do I expand this thing out to account for all members of the domain, to all variables of the domain? I got to include a C term, then I got to include a D term. Okay, and that's kind of how you do it. You do the C first, then the D, or the D, then the C. Doesn't matter. Since this involves a lot of rewriting, let's just kind of stick just to that term and realize that all the other ones are not changing. Okay, and then we'll rewrite everything. So what I'm going to do is I'm going to multiply or AND A and B with 1. What's 1? How about C or not C? What is that? I distribute not A and B into there. So I get not A and B and C, or not A and B and not B and not C. Have I accounted for all of the domain yet? No, because there's still a D term I need. So that sounds like I got to expand each one of those out. Okay, this gets kind of a pain. Okay, that's why I showed you the shortcut. So now all I got to do is multiply each one by 1. What's 1? How about D or not D? Imagine those textbooks which you might be using. D, E, and F terms. Yeah, that's a pain. Distribute it through, not A, and not B, and it with C, and it with D. Or not A, not B, C, and it with not D. Or doing this one now. Not A, not B, not C, and with D, distributing that not A, not B, not C, not D. Now realize this whole time that I've been expanding this thing out, those other 3 product terms have not changed. So I've got to rewrite this whole thing. I mean, it's taken up like 2 screens. That's a single expression right there. Let me go ahead and check my work. Okay, looking good. Look at that thing. Try to write that in VHDL. It will take you all day to do it. Now, try to put this in a truth table. And it's really, despite how long this thing is, it's actually pretty easy. Is think of these things. When will that product term give us a 1? If this is an AND gate and it wants 1s on its inputs to produce a 1, and that's A, and that's B, and that's C, and that's D, what is the combination that gives us that? Well, just read the expression. It's A ANDed with not B, ANDed with C, ANDed with D. That's 1, 1, 1, 1 there, but it's 1, 0, 1, 1. So anytime you see a not, just put a 0. Anytime you see the regular and the non-inverted, put a 1. Just use that technique. Okay, so A is not inverted, 1. B is inverted, 0. C is not inverted, 1. D is inverted, 0. Do this one. 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1. Keep on going. 0, 0, 0, 0, 1, 1, 0, 1. And again, we are staying in the order A, B, C, D. You can do this in any manner you wish. You could do this in A, B, C, D. You can do D, C, B, A. You can do B, A, C, D. Don't do that. Don't do that. Just stay in one order, because ultimately those combinations, which we just created right there, are going to be the combinations in that order, A, B, C, D, for the truth table ordered A, B, C, D. If you want to do it backwards, by all means, try it. You're wasting your time, putting a lot of effort into it. Just make your truth table A, B, C, D. And in the combination, 1, 0, 1, 1, put a 1. In the combination, 1010, put a 1. Get what I'm saying? Okay, I'm going to go ahead and make a list of all these things here off to the left-hand side. Then I'm going to give you a bare truth table. Bare truth table, get it? So there is our combinations. And again, check your work. I've got 1 product term, 2 product terms, 3, 4, 5, 6, 7. Ideally, I should have 7. 1, 2, 3, 4, 5, 6, 7. There you go. Ideally, I should have 7 ones in my truth table. Where are they? Go ahead and start finding those combinations. Well, where's your truth? Where are the values? Are they A, B, C, D? If you're given that opportunity to open up a truth table, and I cannot stress this enough. You think I am beating this thing a little bit too much here. I cannot stress how important it is to stay organized with this. People have failed the final, and as a result have failed the course because they cannot stay organized. I don't know if they're correct or not because they just can't put things in the truth table correctly. You know, you can do C, D, A, B. Why the heck would you ever want to do something like that? It's already there for you. A, B, C, D. I'll put X. Fine. 1, 0, 1, 1. Put a 1 there. Fine. 1, 0, 1, 0. Put a 1 right there. 0, 0, 1, 1. You get the picture. There you go. There's my truth table. And SOP looks for 1s with 0s for the rest of them. There you go. I've taken my expression, expanded it out, and put it in a truth table. Okay, let's take our original expression. Let's try a shortcut now. Let's put our, you don't have to expand these things out all the time. Like I said, there are shortcuts of doing this. Let's go ahead and put our original expression so you can see what it looks like. Okay, so that was our original expression, and I know we expanded it out into 7 product terms to a full-blown SOP expression. You want to save yourself some time? Try this. Look at this expression. And again, it's a pretty easy one to read. It's an SOP. That's why I say it's the most commonly used. When A is a 1 and B is a 0 and C is a 1, how much you want to bet that this product term here is going to output a 1? So maybe I would look in this truth table and let's make a second column. And that second column is empty and I'm going to call it shortcut. Look for combinations of 1, 0, 1 for A, B, and C and put 1s there. What about the next product term? When A is a 0 and B is a 0. Look, and that's going to give you an output 1 right there. So our output for the whole expression will be 1. Where's A and B both 0? Right there, right there, right there, and right there. Finally, we come to our last product term. When A is a 1 and B is a 1 and C is a 0 and D is a 1, that product term will output a 1. Again, we're looking for 1s in an SOP expression. How about 1, 1, 0, 1? What does the truth table for our shortcut look like in comparison to our fully expanded SOP expression with 7 product terms? It's the exact same thing. All I got to do is just fill in the zeros. If you do that shortcut, you don't have to do it, but imagine how much more time you will be able to devote to tracking bears or hunting bears and making bear traps, okay? What I'm saying, there are shortcuts to this, but that fully expanded SOP expression will always work. Sometimes a shortcut doesn't work. And you might be one of these people that can just look at an expression, even a POS expression, and just instantly spit out a truth table. I'm not one of those people. I kind of like using the shortcut method here, get it down to a minimized SOP expression. But like I say, that other one always works. So we did expression to truth table. Now I want you to do the opposite. And we're going to stick with this same one. I know there was a short version. What I want now is from the truth table to the expression. Let's say you have no idea what that expression was, and someone slapped this truth table down at you. What is the full SOP expression? Let's go ahead and clean this up and just kind of pretend these combinations over there don't exist. Don't look at them. Cover up that corner of the screen. You're just given the truth table. Okay, how do I come up with the SOP expression? Just take the combinations. Take the combinations. What is the combination here that gives us a 1? Well, that combination is 4 zeros, where A is a 0, B is a 0, C is a 0, and D is a 0. What's the next combination that gives us a 1? 0, 1, 0, 1, 0, 0, 1, 1. What's the next one? 1, 0, 1, 0, 1, 1, 0, 1. Okay, whoops, I missed one. Again, check your work. 1, 0, 1, 1. And now let's go to 1, 1, 0, 1. Okay, if those are my input terms, basically come up with the combinations. What do they look like? Well, they're exactly the same as this one's over there, except they're in a different order. So let's go ahead and delete those things. We don't need those anymore. We came up with them. Again, we're looking for the combinations of inputs that give us 1. What do we do with them now? if those are our inputs, we make an AND gate that will output a 1 when we're given that input. Okay, so when we're given all zeros, how do I make an AND gate produce a 1? Invert everything. It's going to look like this. There you go. That's that AND gate with all its inputs inverted. What's the expression for that AND gate? It's not A, ANDed with not B, ANDed with not C, ANDed with not D. That's my first product term. Okay, what's the second product term? Given the combination 0001, sounds like I'm going to have to invert the first three inputs, i.e. A, B, and C, and then I'm just going to leave D alone. What's the expression for that? And you can keep on using this AND gate if you want to. If you want to draw things, go ahead. Straight shot for D, A, B, C, D. When A is a 0, B is a 0, C is a 0, and D is a 1, this AND gate will have 1, 1, 1, 1 on its inputs like you'd expect. It's going to output a 1. What's the expression for that AND gate? It's not A, not B, not C, D. Let's not use that analogy anymore because it's growing tiring drawing AND gates with a bunch of inverters on it. Just think, if there's a 0, invert it. If there's a 1, leave it alone. 0, 0, 1, 0. Not A, not B, leave it alone. C, not D. And that's the third one. Do the fourth, fifth, sixth, and seventh. What you should look like is this. Not A, not B, C, D. A, not B, C, not D. Second to last one is A, not B, C, D. Finally, the last one is A, B, not C, D. Let's check my work. Looking good. I've got 7 combinations that will give me a 1. I've got 7 product terms. What do I do with the sum of products? Or them all together? And I'm going to write that down here. Okay, there you go. That is all 7 product terms being ORed together. Is that exactly what we came up with when we when we had the expression and expanded out? It should be. Let's go ahead and compare them. I'll go ahead and put that the one we started with, because again, we're going from expression to truth table, and purposes of these examples, I'm going the exact same one, truth table to the expression. You should be able to do either direction. Okay, I'm just doing this so we are giving you a chance to compare forward and back. So let's go ahead and put what we originally had here. Okay, there you go. And I even copied and pasted so you know that there's no shenanigans there. Okay, so I didn't just suddenly just rewrite the thing. It's the same expression. It's just in different order. How am I going to figure this out here? Just kind of look for, so that one's highlighted in green. Okay, where's A, not B, C, D? Right there. So it's accounted for. Where's A, not B, C, not D? Right there. Go through and find where these things are. This guy, not A, not B, C, D, right above it. 0, 0, and you can start thinking in these terms. 0, 0, 1, 0. It helps when you're trying to convert these things from binary equivalents, i.e. the truth table, to the actual expression. That's right there. This guy is right there. And finally, this all zeros term, and this guy hasn't moved at all. All terms are there, it's just that they're in a different order. So we came up with the expression that we should have come up with. You can use those shortcuts. You should be able to take a truth table and go straight to a full SOP expression, and you should be able to take a full SOP expression and go to a truth table. This lecture has just been about the habits of the bear. Okay, we have not discussed catching the bear. And the hardest part is getting the bear in the frickin' trap to begin with. That's the hardest part. That's the art form, is actually coming up with how these expressions are going to work. And again, I'm going to put you guys through art school with some systematic exercises to develop combinational logic expressions. We're going to learn in the next lecture all about bear traps, namely the Carnot map.